Okay, here's the example I was doing for you. I'm just going to highlight a few things. I'm probably not going to walk you through everything, but of course, if you were listening and watching, you probably know most of all what I was doing. First thing, you have two separate independent samples. Sometimes kids get this confused with a paired t-test, like the difference, like the one we did a few minutes ago when Josh asked the question, the dominant side versus the non-dominant side. There, I'm looking at the mean difference. Here, I'm looking at the differences between the means. Two different things, okay? And so if you can tell the difference, no pun intended, if you can distinguish between those, then you're going to be in good shape. Guys, basically, they're going to give you two separate sets of data, and you just have to ask, are these independent of each other? And since they are, then you know this is going to be a two sample mean versus just a paired t-test. Okay, and the paired t-test is a little bit more obvious because, you look at it and it's like, one person is going through two treatments, like before, after, pre-post, that kind of thing. All right, so here I'm identifying the two separate parameters. So I call them mu1 and mu2, and I've already told you why I said mu1 was one bedroom apartment, mu2 was two bedroom apartment. Next thing I did was identify the null and alternative. Again, the null is always mu1 equals mu2. Just like in proportions, P1 equals P2. There's no difference, okay? Sometimes in other textbooks, you would have seen mu1 minus mu2 equals 0. Well, if you solve for mu1, mu2 goes over there, and that way they're equivalent. I don't know why textbooks do that, but they just want to make things look a lot harder than what they really are, okay? So this is just mu1 equals mu2. And then where did the ha come from? Well, right here they said the two-bedroom apartment was more than the one-bedroom apartment. So they just want to see if it's going to be more than, but is it significantly more? Okay, justifiably. So that's why we're running that test. So ha, mu1 is less than mu2. Our procedure is called a two-sample t-test. And then I've already hinted around how to do the planning stage. Same things, simple random sample, population at least 10 times sample size. I address both parameters, or both samples there, okay? So at least 100 one-bedroom apartments in existence, at least 100 two-bedroom apartments in existence. We're assuming the independence for each apartment selected is independent, not influencing each other, and then normality, both box plots. You have to do two box plots on both, okay, and make a comment about what you see. All right, so here it says, so some skewness, but no outliers were present, proceed with caution. This piece here, the do part, here's your formula, already addressed that, and again, this is in or on your formula sheet. That's the thing that is given to you, okay? And I reference to you, it's in the middle of the page there. And so there are variances. So you just note that you're squaring them. Again, don't do the math. Write down the numbers, but let the calculator do the math for you. And so I went to two sample t-test inside the calculator and entered in my information. And I came up with a test statistic of this. Now, I did not draw a graph when I was talking to you in Zoom, but draw a stinking sketch, okay? And we have our p-value of being 0.0289, which is less than alpha, so we get to reject it. And I'd made reference to this degree of freedom earlier. I just wrote it down again You really don't need that. It's more if you were using some multiple choice, if we had longer to deal with this, and I'd explain more how this degree of freedom comes into play. It is okay if you use n minus 1, the smaller of the two sample sizes. And so that's what this little piece right here says. N minus 1, smaller of the two sample sizes. So we're doing degree of freedom equals 9. Now, why degree of freedom? Where does that come into play? Only in confidence intervals. I'm not going to be using it right now for a test. Now, the way I concluded this is a little different than what you're used to seeing. Again, if we were in class and we were taking the real test, not saying your test is not real, but the test where you have the full gamut of AP statistics, they'll probably want you to interpret a p-value. And so I wrote the conclusion by referencing the p-value. So this is how you kind of talk about it. If the null hypothesis were true, if indeed that the mean rent for a one-bedroom apartment and a two-bedroom apartment were the same, the chance of obtaining two samples whose means differ by as much as this one in this example, the likelihood of that occurring is only 0.029. And that's just due to chance alone. Well, that is very unlikely for it to be due to chance alone. We want it to be due to, because it's wrong. That's the deal. So because this guy is less than 0.05, we reject the null and conclude that the mean rent for a two-bedroom apartment is indeed higher than the mean rent for the one-bedroom apartment. Now, that is p-value talk. Your conclusion can still say, I have sufficient evidence, because my p-value is less than 0.05, that to reject the null and claim that the mean monthly rent for a one-bedroom apartment is indeed significantly lower than, or vice versa, the mean rent of a two-bedroom apartment is significantly higher than the mean rent of the one-bedroom. So you can write it the way you are normally writing it. It's just that, again, I'm addressing the concept of a p-value, which, when you're talking full gamut of AP stats, they want you to be able to also say that. And it's basically, if your null were true, you're going to get a value as, in this case, low or lower this often due to just chance. Okay, well, it's low enough. See, we're expecting 5% of the time, because that's what our alpha is. But see, we actually got 3% of the time. And so it's significantly lower. So we're rejecting that null. Okay? And then moving on to the confidence interval.